Welcome to Math 2320. This is section 7.6. This is our last section in the chapter on Laplace transforms. In this case, we're applying Laplace transforms to a system of differential equations. And in our first problem here, we have a set of first order problems with some initial conditions. So, we simply take the Laplace transform of both sides. Alright, as you see in these two. And so I've written A for the Laplace transform of x of t and B for the Laplace transform for y of t. So first off, I have the Laplace transform of a derivative, first derivative, so SA minus x at 0 equals minus A plus B. And from the second equation, SB minus y at 0 equals 2a. Alright, so I plug in my initial conditions. Y at 0 is 6 and x at 0 is 0. So now I'm going to put together the things with a's and b's. Alright, so on this first one, I've got a times s plus 1 minus b is 0. And in the second one, move the 2a to the left, the 6 to the right. Alright, so now I've got an algebraic system of equations to solve for a and b, and then do the inverse Laplace transform to get back. Alright, so I'm going to get rid of the b first. So because I've got a plus s, which is pretty easy to get rid of. So I'm multiplying the first equation by s all the way through. The b parts cancel. So for the a parts, I've got this s squared plus s minus 2. Alright, that's factorable, so when I divide by it, I get that a is 6 over s plus 2, s minus 1. So at that time, it's just a question of expanding this using partial fractions. So I'm trying to figure out the constants on the top. Alright, so multiplying through by this denominator, the s plus 2 cancels. I get an a s minus 1 and a b s plus 2. Alright, at that point, I'm just picking values for s to make either a or b go away. S is 1, the a part goes away, and I get b is 2. If s is minus 2, then the b part goes away, and I get a. Alright, so here's my a. Taking the inverse Laplace transform of it, I get x of t. Well, we should recognize 1 over s plus 2 is e to the minus 2t. 1 over s minus 1 is e to the t, with the corresponding constants in the front. Alright, I go back now to one of my equations that was simpler, and I'm trying to figure out now what's a. And I'm going to use what I know. I'm trying to find out b, and I'm going to use what I just found out about a. Alright, so I'll go back to this equation. I'm going to get a on one side by itself. Now the a I'm using here is from this piece. So 2 times that a is I get a 12 plus the 6 stuck on the end there. Divide through by s. Alright, so now we've got this expression. This second piece, I'm going to leave it alone for now and try to work with this first part. With the first part, I'm going to expand it using partial fractions. So I've got 3 linear terms here. Alright, so I'm trying to figure out the constants on the top. Multiply through by this denominator and then cancel the corresponding pieces. So now my goal is to pick values for s, namely minus 2, which makes A and C go away and I get B. If S is 0, B and C go away and I get A. And if S is 1, A and B go away and I get C. Alright, so doing that, I now have A, B, and C. And the first piece is writable as this sum. We still have this 6 over S on the end. And the good news is it cancels with my first term. And so I'm left with only those two pieces, which is now easy to find the inverse Laplace transform because I can clearly see it's e to the minus 2t and e to the t. All right. In question 2, we have a new system of equations. First order, initial conditions. So again, take the Laplace transform of both sides of the equation. Use our properties for the Laplace transform of each of the derivatives. Let's see, my initial conditions are minus 1 and 3. Alright, so minus 1 and 3. So here I had minus x0. That's now a plus 1 minus 3. Now I want to get all the A stuff and B stuff together. Alright, so bring the A part over, the 2B over, move the minus 1. And similarly for the second term. Alright, so looking at this, there's nothing easy to get rid of, so I'm just going to get rid of the A part. Multiply the first one by minus 5 all the way through. Multiply the second one all the way through by s minus 1. Alright, so when I do that, the A part goes away and I'm left with the B part and this stuff on the right. Alright, so here's the stuff on the right. The B part, I've got a minus 10b and I've got this term which is s squared minus 1 and also a minus b. Alright, take out the b and I'm left with a minus 10 and from this part minus s squared plus 1. Alright, the minus 10 and the 1 is a minus 9, but now take this minus out in the front. Alright, so we're to that particular step. I'm just going to write it as a minus 1 so we don't forget. On the right, I've got a minus 3s plus 3 plus 5. 3 and 5 is 8. Alright, so let's see. At that point, I'm going to multiply through by negative 1, making me a 3 and a minus 8, and then divide by s squared plus 9. Looking at this, I'm noticing I can split it, and it does seem like the inverse Laplace transform will be a cosine and a sine. Alright, splitting off the first part. This part's easy. That's the cosine of 3t. For the 8 part, well, let's see. If I'm going to recognize a sine, I need the square root of 9, which is a 3 on the top. So put it there, but divide it out so we don't change the problem. And so I get, for the inverse Laplace transform, 3 cosine t minus 8/3 sine of 3t. Alright, so now it's a question of going back and putting in what I know about b and trying to figure out what's a. Alright, so move this negative term to the right. Alright, fill in b. I've got the 3, so I'm going to get a common denominator here, s squared plus 9, top and bottom. And now I need to figure out what's going on with this first piece. So just multiply it all out. Alright, got that. Bring in the minus 3s squared minus 27. The good news is the s squared stuff goes away. I've got a minus 5s minus 35. All right, so at that point, two things are going to go on. I'm going to take out the minus 5. There's still this 5 multiplied by a. So divide both sides by 5. We get to there. The 5's are going to cancel. And so again, I'm going to split this. So I've got the minus s and a minus 7. First part is my cosine of 3t. The second piece, the 7 on the top, I need to get it out of the way. Put a 3 on the top, divide by that same 3. All right. And so this becomes minus 7/3 sine of 3t. All right, and in our last equation for systems, we have an electrical network. I have E of t going through a resistor and two inductors. Current I1 comes in through resistance 1 and splits into currents 2 and 3. So at that particular junction, I can see that I1 has to be the sum of those two currents. We're not losing current, so it's got to be equal to the sum. The voltage drop through a resistor is IR, so I'll make use of that in each of these loops. The voltage drop through inductors is the derivative of the current times the inductance. And so if you use Kirchhoff's laws, you're going to get E, you're going to get IR, you're going to get L1, the derivative of I2 with t. And so when you clean all that up, you're going to get this system of differential equations. Now they're going to want us to solve this for particular values of R, L, E, and the initial currents. Alright, so what I did was I used the resistance of 10 ohms, 0.01 henries, 0.025 henries. E is a constant voltage source of 100 volts. Initial conditions of the initial currents are 0. So in the first equation, I divided everything by L1, and in the second one by L2. So filling in the values of R, L1, L2, we get our constants for our differential equation. And that appears here in this blue box. Alright, so now take the Laplace transform of everything we see. Bring in the initial conditions. Alright, those come in through the Laplace transform of the derivatives. I'm going to use A and B again for each of the different Laplace transforms. And so, cleaning it up, we now have our system, our algebraic system to solve for A and B. Alright, so I'm going to get rid of A first. I multiply through by minus 400. And in the second one by S plus 1000. Alright, so the A parts will go away. I've got an ugly looking B part. And I've got these right hand sides. Let's take the B part first. I've got minus 400 times 1000. So I'm going to get a minus 400,000. I've got S squared minus 1400s and a positive 400,000. That's good because the 400,000s cancel. And I get something fairly simple here in the front of B. On the right, I've got minus 400 times 10,000. So I get a minus 4 million over s. As I multiply this term by each one of these, first one, the s's cancel and I get 4,000. For the second part, I get a 4 million over s. But that's okay. That term cancels the first negative 4 million. And so we're down to this result for b. But again, I need to use partial fractions. So here's b. I'm going to expand it as the sum over these two linear terms. I just need to figure out c and d. If s is 0, d goes away, and I get c. c is 20 over 7. If s is minus 1400, the s part goes away, and I can solve for d. d is minus 20 over 7. All right, so looking at that, let's see. So I've got 27ths 1 over s. Inverse Laplace transform of 1 over s is 1, so I get this constant piece. This part is a e to the minus 1400t. And this is current 3. So current 3, notice, has a transient part. This part is decaying to 0 quickly because of this e to the minus 1400t. So I'm getting a constant current after a short time for I3. So now I need to figure out what's my A term. So I'm going to fill in what I knew about B. All right, so I've got this term times that. So I'm going to divide through by 400, make this number and that number smaller. So I get a minus 10, and I get a 10 over s piece. First part, I need to split using partial fractions. We're using that often. So multiply through by this denominator. And again, I'm going to pick values for s. s is 0 and minus 1400 to give me c and d. So in the first case, I get a minus 27ths. And in the second case, when s is minus 1400, I get a minus 57ths. All right, so fill in c and d. But we're not done because I still had this term on the right hand side. So I'm going to rewrite this 10 as 70 over 7, combine that with the minus 20 over 7, and so I get 50 over 7. Taking the inverse Laplace transform, I find out what is I2. Again, I get a constant current piece. I get a transient part, which is decaying to 0. So after a certain amount of time, the current in I2 is 50 over 7. What's I1? Well, I1 was split into I2 and I3. So combining the two solutions, I get 70 over 7 minus 70 over 7 with this transient part. That part's going to decay to 0, and I end up with the current, constant current in I1 of 10. And that concludes our section on Laplace transforms.